Hello everyone, my name is Angelique Lentjes. Welcome to our webinar, The Solar Energy Revolution. Are you up to date on this sunny afternoon in the Netherlands? We kick off our Professional Education Week with this webinar, hosted to you by TU Delft Learning for Life. TU Delft offers a broad portfolio of courses for professionals on a variety of themes, including the energy transition. In the next hour, you will be brought up to speed on the latest insights on solar technology by our speaker, Arno Smets, professor at TU Delft. Please raise your questions in the Q&A. We will try to answer as many as we can. Arno, welcome to you as well. Please shine a light on our topic of today.
Okay, thank you, Angelique, for the very nice introduction, and welcome everybody in this first webinar of the Professional Education Week here at the Delft University of Technology. It's a pleasure to share the latest insights and trends and advances in solar energy. So for this hour, I selected some current insights. I'm using some of the latest reports, international reports on the topic, going from the role of solar energy in the energy transition up to, I also will touch up on some of the technology advances as well. And if you think like, oh, this is a very exciting topic and I want to know more about this, I will also show this QR code at the end of this webinar. But here you can check, because we offer a lot of courses online on the topic of solar energy. It goes from introduction level up to levels of professional. So me and my colleagues provide there many courses. Talking about colleagues, here you see my colleagues of the Photovoltaic Material and Devices group here at the Delft University of Technology. With my colleagues, we do a lot of research and on the development of solar energy. And in the last slides of this webinar, I will show a little bit, shine a little bit on the topics which we cover here. So today, first, the main message I want to broadcast here is that the solar energy revolution basically just have started, and it will be a revolution. I think it's a very important technology component of the energy transition. Why do we need the energy transition? So it was already 9 years ago that 196 countries committed themselves to the Paris Climate Agreement. So in this agreement, those countries committed to introducing policies to make sure that we reduce the temperature increase on planet Earth in reference to pre-industrial times to maximum 1.5 degrees Celsius, and at maximum 2 degrees Celsius. And to do that, this is basically the challenge which we are facing. These are the latest scenarios of the Intergovernmental Panel of Climate Change reported. And there they show how fast we have to reduce the carbon dioxide emissions. What you see over here is basically 5 scenarios as being described, and also the result of those 5 scenarios. What would be the temperature increase at the end of this century in reference to pre-industrial time? So if you look at the light blue color over here, that's basically what we agreed on in the Paris Agreement, 1.5 degrees Celsius. You see that we have to start reducing our CO2 emissions right now. And the dark blue line is basically we just pass the commitments of the Paris Agreement. That would end up around 2 degrees Celsius increase at the end. So that we have to establish. And what is the main cause of these carbon dioxide emissions? It's our habit of using fossil fuels. So we have gas, we have oil and coal, and with that we generate electricity, we power the industries, we power our mobilities, cars, ships, and stuff like that. And that needs to change, transfer in a new energy infrastructure in which we do not use those fossil. We use renewable energy sources to generate our energy, and we distribute our energy carriers to the sectors where we need it. That can be residential, can be industry, or it can be to power your vehicle. And what you see over here, that the main energy carrier is going to be electricity, and how to generate this new type how to generate this energy carrier is using renewable energy sources. Here you see an example of a Sankey diagram, and this is a very complex diagram which basically demonstrates the energy infrastructure as we have it now in the European Union. All the colors you see over here are different energy carriers. You see gas, coal, electricity, heat, oil, and the green is the renewable electricity generation. The width of these bars means the amount of energy carrier currently being used, and this energy infrastructure needs to be changed. So basically, the green lines has to become the dominant lines in the next 30 years. And if you talk about such energy systems, so here I copied some pictures on top of this. So where do we use the energy, where it's being consumed? Where do we win, for instance, the fossil fuels? How do we distribute this? In which markets are these energy carriers being sold? You already see that the whole energy infrastructure is a very complex system. And even on all these pictures, I can put companies that somehow have a role in this energy structure. So we're also talking about a big economy. It's a financial model, the whole energy transition. And you can imagine changing that from a fossil fuel base to an energy infrastructure based on renewable electricity generation, and where electricity becomes the dominant energy carrier and also the dominant energy carrier to be used in industry for mobility. It's a big change and a lot of challenges. And these challenges are basically in the financial world. What is the economics behind that? The challenges are in policies. Which policies do we need to support this energy transition? Do we have some sufficient materials to make the components? If we talk about renewable electricity generation, you depend on wind and solar, so there's an intermittency problem as well. So storage becomes an important factor. We have to change the entire infrastructure, so we also rely on human capital. Who is going to construct these new technologies and energy infrastructure? We also need that no one is missing the energy transition. So how do we keep the people on board in this transition? And there are also geopolitical aspects, and also thinking about new technologies. So we can have an energy transition, but should we also not control our energy consumption itself? And what are new technologies and opportunities going to do to that? So this is a very complex picture, and I'm not claiming that I have the knowledge that I exactly know how this energy transition will play out. What I know is that the basis which we have, which is renewable energy generation, that we heavily will rely on wind and solar energy in this transition. So here you see the roadmap of the CO2 emissions, and internationally countries are making plans, commitments to work on this. And to show that we are making progress, I show that in this graph. Here I have from the International Energy Agency, the World Outlook. This is their predictions only 6 years ago in 2019 on different scenarios. And this is, the red line is business as usual. And here you see with all the policies which were implemented 6 years ago, it would mean that basically the CO2 emissions in 2050 would be the same as we have currently. So if I going in these reports 2 years later, or even 3 years later, you see that already more policies are implemented, which you can is indicated by the blue line, where we at 2050 already result in much lower emissions. And Here we're making a lot of progress. If I extrapolate this, it means that in 2043 we have all policies in place to be at zero emissions in 2050. The orange line, which you see over here, are the announced pledges scenario. That means that what the countries have announced what they want to do, but that are policies which not implemented yet to realize that. And the green line is basically the net zero emissions. That is what we should accomplish to arrive at zero. So there is progress, but we are not there yet. And if you think about energy transition, and already mentioned that if we need to use renewable energy sources, electricity will start to play a dominant role in the energy infrastructure. And talking about energy scenarios, one of the pioneers and visionaries in calculating in high resolution, in high detail, in time and in place, energy transition scenarios, the entire infrastructure, is Christian Breyer, Professor Christian Breyer and his group. And what you see over here, this is a visionary paper for where he did at a great detail for the entire world, how to transit from the current energy infrastructure to one which is 100% renewable in 2050. And the green color over here shows that the energy carrier of electricity. So electricity will become a very dominant one. And this model is also even calculated without negative CO2 emissions in the second half of the century. So it means that we do not need carbon capture. And it's based on current technologies which are already existing now. And the most interesting thing is if you see where in 2050 we could be in terms of the generation of electricity, what you see over here, that is in blue, wind, and in yellow, solar will be the dominant electricity generation technologies worldwide. Here you see it more or less in a picture where I identify the penetration depths of solar and wind. And here you also see the paper where it has been published by many experts all over the world. And what you see over here is, with my pointer, I indicate this is the paper I'm talking about. A lot of models in the past have been not very positive in terms of how much of the future electricity will be generated by solar. And in this paper, we discussed that in all these models, they use outdated financial data. The cost price of PV is overestimated and much cheaper. And if you do that, you already arrive at quite high penetration depths. And that is also something strange if you look at solar energy, or what we also call it like converting solar energy into electricity, photovoltaics. It's heavily underestimated all the time. And I will repeat that several times during this webinar. It was also for a long time underestimated by the Intergovernmental Panel of Climate Change. And here you see in their climate assessment models which technologies of the short term can help us a lot in reducing the CO2 emissions. What you basically see here is these bars indicate how much CO2 reductions per year we can achieve using technologies, and the upper bar is wind and this is solar. And what you see together, they can already reduce 8 gigatons of CO2 at the end of 2030, so in 5-6 years. That is already 20% of the total CO2 emissions. So this is the low-hanging fruit. And more interesting, in the color of these bars indicate how much do we have to invest. And the blue bars means that it's even cheaper than what we're doing now. And solar electricity in many places of the world is already the cheapest form of generating electricity. I will come back to that. So wind and solar are very mature technologies, and they, on the short term, play a very important role in reducing our CO2 emissions. Here you see the star over here. This is what if we would accomplish the reductions as shown in the last graph. So it means that we would be almost on the route of the blue line in keeping the temperature increase at the end of this century at 1.5 degrees Celsius in reference of pre-industrial times. So solar energy is a solution, the solution. If you think about all the processes taking place at planet Earth on the surface, the atmosphere, the winds being generated, the rain, the waves, even life, the energy source for that is sunlight. And it is also then a no-brainer to use that to generate our energy needs. And as I mentioned, solar energy is heavily underestimated. I started my PhD on materials which you can use for photovoltaics to convert sunlight into electricity in 1998, so 27 years ago. And if I look then in the World Energy Outlook from the International Energy Agency, they were predicting that photovoltaics would maybe generate a few gigawatts of solar electricity in 2024 last year. If you see what has been accomplished, it's a factor of 500 more than was estimated 25 years ago. And there you see that in this technology, based on semiconductor materials like crystalline silicon to convert solar energy into electricity, we made enormous step in first improving the performance of this technology, and secondly, in making it very cheap. And what you see over here, the yellow line is the total cumulative installed power of PV worldwide. So it's 2,200 gigawatts, and currently we're already using the terawatt. So that is a 1 with 9 zeros, 2.2 terawatts of installed. What you also see in this graph are the red bars, and that is the every year annual added power to generate photovoltaic power added to the system. And if you look at 2 years ago, in 22, we surpassed the 1 terawatt border. And what you see already is that now 2 years later, we installed just as much as it took up to 22 to install the same capacity. And you see that this is not a linear dependence, but it still looks like an exponential growth rate. So it's still accelerating. So it is mind-blowing what basically is happening over here. To put this in perspective, I compare it to other renewable electricity generation. Here you see hydroelectricity. So in the late 19th century, when the Francis turbines were developed and invented, small hydro dams were built, and here you see how it has been scaled up during time. Here you also see the nuclear technology, so nuclear plants to generate electricity. You see how they are coming up in time and how they at a certain point are stabilizing. Here I show the wind electricity and photovoltaic, the solar electricity, how they are coming in. And I showed you also, for instance, the energy transition model. So to achieve this 70% of contribution of solar electricity in 2050 to the total energy transition, it means that we have to follow this line. Having said this is a logarithmic scale. So what does that mean? That means that the coming 5-6 years, the annual installations or the production capacity of photovoltaic modules needs to increase every year by around 30-35%, as it has been doing for the last 25 years. So if we achieve that point up here, it means that we have a technology available what we can scale up then without increasing anymore the production capacity to a situation where we can generate 70% of our energy needs with only photovoltaics. And what you see over here, that basically we're still scaling up very fast and we're still very close to this red line. So I mentioned it is possible, and we are still very close to the trend to make it happen. What I show here is the effective power, so it means that I also have compensated for the capacity factor. That means what is really being generated by the technologies. So if we talk about, okay, if solar is going to play a big role, will that be the case everywhere around the world? No, there are differences per region. Let me take, for instance, the example of the Netherlands. The Netherlands over here, we are in Northern Europe. We are on a latitude of 52 degrees. And it means that we have very long days during the summer, and during winter time we have only a few hours of sunlight. So in terms of irradiance, there are big seasonal fluctuations. So solar energy cannot do the job itself over here. So the Netherlands luckily is located next to the North Sea, and if you look at wind energy, it's complementary to the solar energy. So in summertime, we have a lot of sun. We don't have hardly any wind. And the other way around, we have a lot of wind in wintertime and not much sun in summertime. So if you think in terms of 100% renewable energy infrastructure in regions like the Netherlands, we will have something like 50% generated by wind and 40% of the electricity generated with PV in those visionary energy transition scenarios, which are based on current existing technologies. And if you look at that, it's also a nice way to check what is the general opinion of policymakers in your own home country in reference, for instance, to these type of energy scenarios. So let me take the example of, for instance, the Netherlands. Here you have last year the government published a report about how to move to a sustainable future, and that also includes the energy transition. And of course, in these, a lot of assumptions are included over there. And if you look in a report like here said by the Dutch government, by the Agency of the Environmental Urban Environment, basically, if I translate it correctly, here you see how the energy infrastructure would look like in the Netherlands. And what you see over here, they predict a certain amount, 24% of the electricity would be generated by photovoltaics. That's still very low if you compare that to the graphs which I showed over here. Even if you see what we have accomplished currently, around 20% of the electricity is now already generated by PV, which is a total net installed nominal power of 27.5 gigawatts. So it means that in 25 years, we only have to 4 to 5 times increase the total power of solar electricity in the Netherlands. So is that ambitious? No, that's not very ambitious, because if you looked at, for instance, to the plot I showed over here, this is what the governments think, and this is what we predict in typical energy transition scenarios based on current technologies. And you see that very often that the role of solar energy is underestimated. And the power of solar energy is also, if you see the exponential growth, it's a modular technology. It's based on solar panels. They can be transported by every car. If you have a tuk-tuk, it means that you can bring the solar panels to the site to be installed. It's very modular, and it can be scaled up relatively easily, distributed and installed in many regions around the world. So then the question is also like, how do we install it? Which surfaces are we using? Where do we put the panels which convert the solar light into electricity? And here you see, for instance, a vision document of our PVMD group at Delft University of Technologies, where we see that in sustainable cities, in an urban environment where you have a lot of buildings, a lot of shading of the sun, you have to have smart solutions how to integrate the PV modules. You can also think about industrial buildings or industrial campuses where you have a lot of roofs where you can install certain technologies. We can think about mobilities, so integrating it in trucks or in cars or in trains or on the stations. The residential integration of PV, or even combining it with agriculture land. So having dual functionality. Can we put panels on agricultural land and still grow crops and harvest crops on there. So smart integrations, and that's something we are looking at, and also how to distribute it to other players. And if you think about in terms of photovoltaic systems, it can be very rural. There where you don't have an electricity grid, just a normal photovoltaic system with a battery is very cheap and already can improve the living standard locally a lot. But you can also think about covering surfaces of big industrial or public buildings, or you can even think about large-scale utility, put it on land to generate a lot of renewable electricity. So there are various ways how to integrate. Having said that, doesn't mean that there's no discussion on governmental or on public level on this topic. So do we want to, which land area do we want to use for that? If you, for instance, here in the Netherlands, the situation is that the population density is quite high. We don't have that much real rural areas. We have 400 citizens per square kilometers. So it means that per person, we only have 50 by 50 meters land area. On that, we have to live. On that, we have to grow our food. On that, we have to build our infrastructure. On that land area, we have to generate our energy. And that is, of course, a discussion where to place it. So at the moment, the policies in the Netherlands is we prefer to first put photovoltaics on the roofs of buildings. Interesting is a recent report of the European Environmental Bureau, and they are looking into where to place it. What is the land area we have available in Europe? And Europe has a relatively high population density as such. And what you see over here that the lands suitable for putting renewable energy sources is 5.2% in the whole Europe. What do we need for this energy transition? Only 2.2%. So in terms of land area, there is sufficient land area around. And if you look at where is this land area, logically, it's most in the rural areas there. So there, the majority will or has to be used to facilitate our renewable electricity generation infrastructure. Then if you see policies of governments, strange enough, and the Netherlands is one of the darkest places on the planet. If you look at the amount of photovoltaics installed per capita, we are a country which has, together with Australia, almost the same amount of nominal power installed. It's 1.5 kilowatt of PV power per person. And the reasons for that is that we, for a long time, had a net metering policy. So residential PV systems, it means that solar electricity, I generate my own photovoltaic system at home. The electricity I'm not using myself, I can feed back to the grid, and I get the same price for that as the retail price I should have bought it from the grid. So that is a sponsoring mechanism for photovoltaics. And that has been in place for a long time, and it will be abolished in 2027 in the Netherlands. And we also have subsidies to support large-scale utility. It's a more tender structure. I will not going in detail exactly how it works, but that has the last 8 years were important incentive to let the PV contribution to the electricity generation in the Netherlands grow. In the Netherlands, 20% more or less of the electricity is now being generated by photovoltaics. A little bit more than 50% is renewable, so the rest is wind and biomass as such. Now it's being abolished, and at the moment, businesses are struggling because the policy is being changed. So net metering will be abolished. So at the moment, we see a dip in the residential sector. Photovoltaics have, for the moment, a more negative frame in the media. But let's compare it, for instance, to a neighbor which did not have any net metering for a very, very, very long time. And if I look at, for instance, what has been installed over there, it's 1200 watt peak per person. It's 80% in reference to what has been installed in the Netherlands with these enormous incentives provided by the government. So what you see is that policies do not play a very big role in that. What mainly plays a role is the technology itself, and that the technology is becoming very cheap. These infrastructures and investments in that have a very good return. It still has a larger return than if you would put the money, for instance, in the bank account. Also, very interesting, I will come back to that, role of batteries. Here we have 82 watt hours of person. That is the total battery capacity installed in the Netherlands. We did not have any incentive for batteries due to this net metering policy. If you see in Germany, they did not have these policies, so they're already installing photovoltaics together with a battery system makes sense, because then it would have a higher return, or it was already more culturally accepted to combine a battery next to a PV system. And what you see over here, there's already 80% more capacity per person installed over there. Another problem, it's a challenge. Here what you see is that as there is so much photovoltaics installed in the Netherlands, the grid starts to have problems, congestion problems. It means that there are moments in time that too much photovoltaics is injected into the grid, and the grid cannot handle that anymore. We call that congestion. Having said that, is that a problem? Let me show here, for instance, a medium voltage grid or cable in the Netherlands. So that is transporting electricity, and the blue line is more or less the load during the hours of the year. So 1 year has 8,760 hours. What is showing that only a very few hours a year, maybe 3, 4, 5%, the capacity, the grid is used full capacity, while most of the year it is used much less than 50% of the capacity. So on average, 50% of the capacity is being used. If you think about, if we could allow some peak shaving over here, let's say if we only would have 10% peak shaving, for instance, by introducing batteries where you store some of the electricity at the peak moments, it means that you can already increase the utilization of your electricity grid infrastructure with 10%. So batteries versus putting more copper cables into the ground, that is a mechanism what we're going to see, because people are talking about we should increase this capacity. No, those batteries are coming there also very cheap, and I will show that in a few slides. Because talking about cost price, the success of solar, it has become very cheap. And for that, you have those learning curves. As you see over here, we have the module cost price, and here we have the cumulative production. And what you see over here, there's double logarithmic plots. Here, a learning rate of 40% means that every time the cumulative production is doubled, the cost price of the PV panel will reduce with 40%. And we as human beings, we cannot think in those double logarithmic plots, so because it means it's getting cheaper and cheaper and cheaper, and much faster than everybody expects. Everybody thinks like, oh, a big step has been made, now the prices will stay the same. No. Continuously, those prices of PV panels have been dropping. If you compare it, for instance, if I want to have a parquetry floor at home, if I go to the wood shop, I have to pay 20 to 40 euros per square meters for the parquet. For construction wood, to build a fence in the garden in the Netherlands, I have to pay 20 to 40 euros per square meters for the wood, the construction wood. If I look at a solar panel, the solar panels are sold over here for 16 to 24 euros per square meters, and even current prices, it's even lower than what I show over here. So even if I want to build a fence in my garden, it would be cheaper to use solar panels than wood, and even not by connecting the solar panels to any grid. So it's mind-blowing how a device based on glass, semiconductor material has become that cheap. And as I mentioned, congestion problems, net metering, that will be abolished, or if you have a battery, a cheap battery, that will solve a lot of problems and also will accelerate again the integration of photovoltaics. What is going on with the batteries currently? Batteries has been mainly upscaled for the electric cars. The last years, we also see that the fraction of production for stationary batteries, stationary storage, is increasing a lot. And here you see the total battery cost prices. Of course, there are different type of batteries, and it's not one-to-one comparable. And here I constructed with various data the same learning curve, which is well known for photovoltaics, but has not yet been used a lot for the batteries. And what you see here, again, double logarithmic plots. And I look at the learning rates, what you see, and the current learning rates over here. And certainly if I look at the learning rates, what we see now this year, last year, and the coming year is 48%, which means that every time the battery capacity is doubled in production, the cost price will halve. And that is not a lot of people realize that, but cheap batteries are coming to the markets very, very, very soon. And that will also change the electricity market. That also means a photovoltaic battery system in small and large scale will become a very cheap solution in reference to other technologies. Here as a comparison, there was the learning curve of the photovoltaics. If I shift that over that of the batteries, it's following the same trend. So I predict that cheap batteries, stationary batteries, coming very soon as well, and that will show similar trends like this. I was talking now more or less the role of the energy transition of solar in this energy transition. I was talking about how cheap it has become and upscaling technology. I want to quickly talk about the technologies itself. And if you talk about photovoltaics, photovoltaic modules, the dominant technology, it's around 98%, is crystalline silicon based. It's based on pieces of crystalline silicon wafers, which from which devices have been made, which convert sunlight into electricity. And those wafers are usually interconnected in a module like this, and that is what we call a photovoltaic module. And this is how the value chain looks like. Silicon is a dominant material, and that so it's winning from mines the silicon quartz side, which is a silicon oxide, and you have to strip the oxygen from them to make pure silicon. From this pure silicon ingots and pure silicon wafers are being made, and those wafers they are being used as a basis to make the solar cells, and the solar cells, they are assembled to modules. And this value chain that happens over around 4 factories of production, and that can happen in different regions in the world. And if you now look, and if you look at PV modules available, either they call them PERC, or for instance the TOPCon, or the heterojunction solar module, they all look the same more or less. So quickly I will dive into what are the differences between these technologies. So here you see the old workhorse. This was the basic technology which was around, and it was called the back surface field. You had here, this is the silicon wafer. This is a back contact of aluminium, and you see here some silver front contacts. And when light is absorbed by this layer, it generates charge carriers, and those charge carriers you have to separate and collect at the contact. So the charge carriers are basically the current. And this device, depending on the operation conditions, generates a current and a voltage. Current times voltage is power, so electricity. This was a very simple technology. If you want to improve the performance of these devices, what is the problem? Very simply said, it's if you look here at this the semiconductor material over here, crystalline silicon, or the metal which you have over here, at this interface, you have a lot of defects, and it means that you have recombination. So charge carriers are getting lost there. It means that you lose current and you lose voltage, you lose power. So you want to prevent of having such interface in the device. And if you look at the advances the technology has made the last 30 years is fighting this loss mechanism. If you look at, for instance, the PERC technology that is at the moment a large part of the market, is passivated emitter rear contact. Basically what you have did, the trick was, if this surface over here is the problem, let's make this surface much smaller so you have point collects here where the current is being collected off the solar cell. And this is an innovation which already improved the efficiencies of the solar cells. Then currently a technology which is taking over of PERC is the TOPCon. So here it looks like that the semiconductor is in contact with this metal again, but here a magic silicon oxide buffer layer has been put in between, and there we make use of a quantum mechanical property, which means that the charge carriers you want to collect, they can tunnel through this layer very magically, and the ones which are not collected over here, they are reflected from this interface. And such you don't have any losses at this interface. It means that you can create high voltage and high currents, very simply explained. Another trick to do that is by using a semiconductor material which has a higher band gap. It means that it can create higher voltages, and by putting that on the other crystalline silicon, you can also create a kind of tunnel properties over here, similar like the TOPCon, and selectively either collect the positive or negatively charges we refer to as the holes and the electrons. So that is basically very simplified the progress being made, and I will come back to that, what that also means in performance. Then, of course, what you see, you have contacts at the front side, at the back side. An innovation is to put cells with all the contacts at the back, where at one side you collect the negative charge carriers and on the other side the positive one, and that is called interdigitated back contacted solar cells. You can also think about making the front side not only transparent, also the back side. So this is, for instance, what you see here, monofacial as they call it, and this is bifacial. So also light scattered from the back can be absorbed in the solar cell and enhancing the performance of the solar cell and the module. And then here you see also a metal wrap tool. You can put, for instance, the front contact through the cells contacting, and you can use this back sheets of a copper where you reduce the current resistance losses as much as possible. I mean, all kind of innovations. I even did not show here the shingled construction and stuff like that. So a lot of innovations over here. And what you currently see, that also a lot of these innovations are being combined in a cell and in modules. Just to show what it means, progress of performance. So here I'm talking about conversion efficiency. That means that the amount of power of solar light incident on the module, if you have a conversion efficiency of 70%, it means 70% of the power is converted in electric power. And here you see, for instance, the old technology, the back surface field. Here you see the PERC technology. Here you see the TOPCon type, the heterojunction ones. And here the orange one is IBC. And here you see the projections which we had as a community a few years ago. And here you see what we already have achieved. Even the advances in conversion technology of the technology is going much faster as we expected. These are examples of modules in production. On the lab level, there we have the record conversion efficiencies. So if you see, for instance, the back surface field, which I introduced, it's around 20% conversion efficiency is the best achieved. If you talk about the PERC type of technologies, it's around 25% the best. If you talk about the TOPCon, it's around 26, 27%, the heterojunction 27%. And now even combining these technologies with an interdigit back contact, even 27.4% is the best conversion conversion efficiency for a crystalline silicon technology. 27.4%. In theory, if you would not have any losses, you could get a conversion efficiency of 29.3, 29.4%. So we are very close to the theoretical limit. So the question now is, what is the progress further? Is there more than the crystalline silicon technology? One route to go is not using silicon, but for instance, much thinner films, thin films. And here you see some random selections are made of companies. Here, the biggest producer of PV thin film modules around the world is using a calcium material, cadmium telluride, and that is First Solar over here. Other example is, for instance, CIGS Solar Frontiers company used to produce in Japan. We have, for instance, Alta Devices making use of 3,5 gallium arsenide type of materials. Here, Highest Solar and thin film silicon flexible module. And here you see an upcoming technology that is perovskite, and Renishine Solar in China is one of the companies which has the first perovskite modules around. So the conversion efficiencies of these technologies, if I talk about of the glass, for instance, cadmium telluride, CIGS, or the perovskite, are still smaller of that of crystalline silicon. Having said that, less materials and a cheaper value chain can be used there. Here, I want to highlight is that all PhD students here of my research line, Hiren Tan, is currently one of the leading figures in the Renishine Solar and the company which is making perovskite modules, making many advances in over there. So currently, they are approaching the 20% conversion efficiency for this technology. Another thing. Yes.
Arno, we also have some questions from the audience, and I know you can easily fill up 2 hours.
Yeah. So give me 5 minutes to finish this topic.
Sure. Yeah.
And then we move to the questions, because else I have to answer this question: where is silicon going?
Yeah.
The silicon is going here. The perovskite technology, you can combine that with a silicon solar cell, and if you combine that, you can go to efficiencies higher than 30%. And that's what I see over here. There's 35 and 36% of the typical tandem solar cells. And if you look at the value chain, currently, if you look at the production, a lot is going on in Asia, mainly in China. So here you see that on wafer, 98% is being produced over there. Module assembly, around 85% is done. But a lot of activities in the US and in India are also scaling up technologies. And in Europe, we hope to do that as well. So thinking about industrialization. And the last topic I would like to address is the circularity. The current technologies, if we want to upscale that to 3 terawatt, is basically what we need in this energy transition model. The red squares over here show the materials which we use. And this is what we would be needing. So what you see is that indium and silver is out of the question. So we also have to think about using less materials and using smart metals to do exactly the same. And that is what we're doing in the Netherlands. We have a big national growth fund to make a circular solar modules, the next generation technologies. You see here flexible falls based on perovskites, building integrated PV. That's what we are doing in the Netherlands. And here you see, and that is what we're doing in the Delft group with all my colleagues working on these technologies. To conclude, I guess we have some questions, Angelique.
Yes, we do. I will bring them to you. When is tandem cell tech for solar panels expected to be a reality for field applications?
So the question is, if you look at the tandem application, so they are looking at here the tandem, the perovskites on top of the crystalline silicon. So currently, there are several companies in Europe. It's Oxford. In China, you have some companies who are bringing the first modules to the market. Having said that, I did not have time to address the topic of reliability. Crystalline silicon is a quite reliable material. Perovskites in the lab is still not as reliable. It means it degrades more. So a lot of work and research is being done to improve the stability of the perovskites. So at the moment, the first productions are there. They are tested in the field. It's looking into the crystal ball. So when and how fast this will be penetrated in the market, and also how fast the reliability will be the same as the crystalline silicon. That's a question. If I could answer that, I know where to put also my model in the current production. A lot of efforts is there, but in my knowledge is that we have always been surprised a lot by the advances being made. So the first modules are on the market, not in the large scale. So if you look at what is mainly available in the coming years, it will still be the crystalline silicon modules, the TOPCon, and maybe the heterojunction technologies. And hopefully we will also see faster, more higher efficiency of the tandem cell introducer. So it's a question with an open end.
All right. Another question we have here is, why does the majority of land used for PV must be agricultural land? Would it be more sensible to use land and buildings in urban locations where the electricity is being used and thereby reducing lost electricity through distribution?
Yes, that's more or less reflecting on this study. What you see, for instance, in the Netherlands at the moment, we have already a relatively high penetration depth of photovoltaics, but far not enough to support an energy structure of based on 100% renewable energy. If you think in terms of decarbonizing the industry, decarbonizing the mobility sector, decarbonizing energy utilization at home and in buildings, heating and cooling, we need a lot of electricity, and we still need to install a lot. And it means that if we talk about the 2.3 surface area which we need in Europe to achieve that, you cannot only do that on roofs and on roofs and buildings. Of course, we should use every facade and roof as efficient as possible, but you also need to use some agriculture land. And I know also in a discussion, and it's in politics at the moment, like if you look at the land area in the Netherlands, 50% is used for agriculture land, and 1/3 of that, so of 2/3 of that, so 1/3 of the agriculture land in the Netherlands is being used to produce food for the cattle, for instance. And even that does not support all the cattle we have in the Netherlands. But even there, using 2% of that surface makes so much possible to achieve a sustainable agriculture sector, to achieve a sustainable sector, that in my view, it's a no-brainer to use that for energy generation. And in Europe, we would not starve from hunger if we would be doing that. So it's a must. If you see, we need that much of energy, and the surfaces in urban areas will at the end not be sufficient. At the moment, it might be, but we also have to realize that we have to start using these surfaces, and it also means then you have to have the infrastructure there ready also with grids. As I already mentioned, the example with batteries, of course, generation and consumption should be matched locally, spatially. So that would require the least grid infrastructure. And there I fully agree.
Okay, good. And what are the advantages and disadvantages of use of femtosecond welding in solar infrastructure?
So I believe this is if I understand well, this is a question which talks about construction of supporting constructions of PV panels, if I'm correct. So that's a more too much detailed question, so that we can discuss that at a later
okay
time. Yeah.
Fine. Yeah. There's also someone who would like to know what your opinion is about nuclear power. Is it still necessary to achieve our climate goals of decarbonizing the economy along with solar and wind? This is especially during this time in which smaller modular reactors are being built and a lot of energy is required to power the AI revolution that we are currently experiencing.
Yeah, so it's a question you get a lot. Certainly, if I'm giving presentations in the Netherlands, if you look at nuclear energy, and I'm going, I have at the back a slide on that one here. Here is the World Nuclear Industry Report, and if you look at nuclear energy itself currently, it's the most expensive technology to generate electricity. And what you see here, the overall conclusion of this report is, contrary to the widespread perception, nuclear power remains irrelevant in the international market for electricity generation technology. Solar plus storage might be the game changer for the adaptation of policy decisions to current industrial realities. So if you look at, for instance, the next slide, do I have the slide here? Oh, that was the slide. This is, for instance, new installed electricity generation. And what you see over there, that nuclear, that's the red, does hardly play any role. The reason for that, it is very, very expensive. Even what I showed you, the learning curves, PV and battery storage, is getting cheaper. If you look in the energy transition models, for instance, what is showed by Professor Christian Breyer, their nuclear is also not needed for the load. It's the sector coupling, battery utilization, and a subtle seasonal fluctuation of using green hydrogen can do the job. Another thing is, nuclear energy is the only electricity generation technology which has an opposite learning curve. Every year it's getting more expensive. So even in the big projects around the world, none of them are based on private money. All existing projects, or the majority, is based on public money, because the financial world does not believe in this technology. So I'm not saying that nuclear is not an option. I'm just looking at the trends and how in international energy transition scenarios, nuclear is not really being considered. Of course, there are a few projects around the world, but these are still marginal in reference what you see here to the yellow and the blue column.
Then we have a question, what caused the learning rate improvement interruption that was seen in both PV development and battery capacity?
Yeah, let me go to the slides. So there you see a bump appearing. Let's see, that's a good question. So here, let me show that for photovoltaics. So what you here see, you have a learning curve. And so when it was a relatively small technology with a few companies being produced, you had a learning curve of 24%. Here we see a bump, and then you see a very hard decline. So in this transition was that in this phase, for instance, crystalline silicon is the dominant technology. The source material over here, the scale of production was such that the source material of the crystalline silicon was basically the waste of the semiconductor material, which is also using crystalline silicon for chips and everything like that. At a certain point, the scale became so big that the needs for crystalline silicon was larger than the semiconductor industry. And it means that the silicon production needed to be scaled up. So there was a shortage in silicon. So what you here over see, this is the transition in which the silicon production, so going from the quartz side to the polysilicon to the ingots to the wafers, needed to be scaled up, and there was a value chain which had to build up. And that shows here the hiccup. But after that was established, it means that the whole vertical value chain was secured, and it was mainly in Asia, which also allowed them to achieve learning curves which are much faster as such. And in batteries, you see the same thing going on. At the vertical value chain is now completely owned by the main producers, and then you see even the acceleration over there. So funny that it's exactly this. You see the same hub over there, but this is how it appears to be the transition from a small to a very mature industry, where all the materials being used over there, they are the dominant user of that material.
Shall we do one final question and conclude this webinar? We are past 5 o'clock CET time. With TEC, thermal energy generator, been around for quite a while. Will this not be another alternative compared to PV, since it operates with heat and require drastically less maintenance and more rugged? Any thoughts?
So, the solar thermal, or what? Sorry, Angelique, what did you?
Thermal energy generator, TEC.
Now, every form of energy utilization is so. I did not stress that, but what I showed you in the Sankey diagram, heat is also a form of energy, and I did not address that. So smart thermal solutions for heating or cooling, or even to be used in industry, or thermal heat for industry, which can be used for heating of neighborhoods. All these solutions will be part of the future energy infrastructure. So every technology will contribute to that. Also heat sources, what I showed over there, although I was talking about 69% of solar, for instance, in the energy transition model of Christian Bayer, 80% of wind, there is also a fraction of heat sources in there, and certainly that should be used. Talking about decarbonization of the sectors, industry, mobility, or residential, then still electrification of processes will be an important role, and that's why solar electricity will play a role. Another thing is that some of the thermal technology sources, they also don't have that much power density per area. So then photovoltaics is preferred as such. But it's not one technology competing with the other one. We need all the solutions there. And depending on the location, the application, some solutions will be better than others.
All right. Well, I think we should conclude this webinar. Maybe a final thought, Arno?
Yeah. So it was called the solar energy revolution is just getting started. And what I showed you, it's just the modeler. We have those modules, and they can easily be installed everywhere. It's power to the people, basically, and that is people underestimate what type of revolution this will be causing. And in the Netherlands, 20% of the electricity is now generated by solar electricity. Worldwide, on average, it's lower than that, but these numbers are coming very fast at us, and the penetration of solar electricity will become very dominant. It's something which is happening very fast. And also, if you think about the rural areas in the world where there's no, or the costs are too high to have an electricity grid over there, small DC microgrids powered by solar electricity and with storage is a game changer as well. So power to the people, and there will be solar electricity.
Excellent. Well, and thanks everyone for joining us. And if you want to hear more or see more of Arno, we offer also online courses on solar energy. So please visit our website and see what we have to offer you. Thank you, Arno, for the insightful presentation of today, and thank you all for joining us. If you have any questions, please reach out to us. And if you would like to follow us, we are on our socials, on the socials as well. Thank you.
Thank you.